Yes, you guys ready? So today I'm not going to show any pictures, okay? I'm just going to do a straight up lecture just to convince you I can do it without bells and whistles, right? I'm going to remind you, I gave you a very simple problem on predicting critical points for simple fluids. Please look at that problem. This is just trying to remind you of the kind of things you do, not in StatMech, but in thermal, right? So today's plan is sort of going through a lot of math. I started yesterday with this idea of assembling surfactants, right? So I built a molecular thermodynamic theory. I sort of got halfway through it. So here's what we did, for example. We had entities like this. So there is a hydrophilic head, a hydrophobic tail. You put it in water. This thing at very low concentration will dissolve because of entropy, translational entropy. As you raise the concentration, what happens is that the hydrophobic chains hate the water. They realize they can come together by eliminating the water so they can put the chains on the inside of a micelle. And this way they can save energetic interactions. And this transition is called a micellization transition, aggregation transition, self-assembly transition, whatever you want, okay? So that's what we wanted to build. And I'm using a formalism that goes back to 1976. It's by this guy, Jacob Israelashvili, who wrote a book on the topic. It's really a spectacular book. But also as you go through it, you realize it is wrong. Okay, so I'm going to give you the formulation. I'm going to do it wrong. I'm going to tell you why it's wrong. And then I'm going to try and fix it. That's going to be the roadmap for what we do today. Okay? So I'm going to remind you what we did. What Jacob did was, he said if this guy wants to go, starting out as monomers, so a single surfactant molecule sitting by itself, I'm going to call a monomer. I don't know why I'm getting feedback. Everybody okay? Can you guys hear me properly back there? Yep, okay. So a single surfactant, the monomer, then it can form dimers, trimers, blah, blah, blah. And really what you're focusing on is the formation of things like that. And you want to understand the aggregation number, the number of molecules that go into form an aggregate. It could be a sphere, cylinder, lamella, whatever. So we used a molecular thermodynamic formalism, and just sort of reminding what I did. And at the end, you said that the chemical potential of the chain as a monomer must equal that, I call that an A, must equal this, must equals that. And this formula is called the law of mass action. And then you broke this up into what I call a reference or a reference state chemical potential and an ideal gas translation entropy, which at the end gave an expression that looks something like this. It said it's going to be N x1, that's the monomer concentration, the exponential minus, I defined this quantity here, and I'll tell you what that is in a moment. So mu n0 prime is the chemical potential of an n-mer divided by n, so that is the chemical potential of a chain in an n-mer in the standard state. And then what Jacob did was he said, I'm going to assume that the only thing that drives aggregation is enthalpy. And so in that context, if you start thinking about a linear aggregate, you can show that mu n0 prime is going to look like the energy Everybody remember all this stuff? This is where I left off yesterday. So epsilon is a number. In Chandan's number, it's going to be a number greater than 1 because that's what's going to drive things to aggregate. Okay, if it's smaller than 1, translation entropy wins. So epsilon is going to be greater than 1. N is the chain length of that. And you can actually go through and do a similar calculation, and I'm not going to bother you with the details of this, that if it forms disks, for example, you can do a similar calculation, and then you will get that mu n0 prime will go like, again, epsilon kt minus 1 by 1 over n to the 1/2. And for a sphere, it'll go as 1 over 1 n to the 1/3. So it's the fractal dimension of that object, 1 over the fractal dimension of the object, is going to tell you what fraction of neighbors are missing. Okay? So generically, for any class of systems, you can write that mu n0 prime is going to look like minus epsilon kt, 1 by 1 over n to the power of p, where this p depends on the kind of structure that you form. It's 1 for rods, a half for disks, a third for spheres. And remember, you want to form spheres, which are those micellar structures, and so the structure you're thinking about, the canonical structure for surfactants, is going to be P equals 130. Okay, so let's plug this guy back into this equation. All right? And I'm not going to actually do the calculation. You can do that. When you actually plug that in, you're going to get this formula. So you start with xn. It's n. x1, that's the monomer concentration. E to the epsilon, the kts cancel out, minus epsilon over n, all to the power of n. This is just for P equals 1, this is for rods. So this gives you this very nice, simple formula. Yes? Go ahead, ask Srikanth, I'm listening. Right? Correct. Yeah. So what he's basically saying is, I'm not going to think about as surfactants. I'm going to think about objects that want to assemble, right? And the only thing driving assembly is energetics. So if I'm sitting on a disk, then the layer of things that is missing, the contacts, will go like the perimeter, which is going to go as R, but R is n to the 1/2. So the fraction of missing neighbors is going to go like that. So it doesn't say anything about the structure of the molecule that's forming a surfactant. It just says there are entities that are driven by energetic interactions to form these structures. It's the surface, the missing, exactly, that's all it is, okay? And again, it's a purely energetic argument. If you start thinking about a surfactant, this argument falls apart, because then you have to accommodate the tails and the heads, right? Everybody following along? Okay, so remember that formula. Look at that thing, it's very nice, right? So the question now is, I say, the fraction of monomers that are in an N-mer depend on the fraction of monomers that are free. Okay? So I don't know what that quantity is. I have to find that out. So what I do is I take a certain amount of surfactant, I throw it in solution. Let's say the concentration is C, right? And those surfactant molecules form all these different entities. Okay? So for me to determine C, I have to satisfy this mass balance constraint. Everybody following what I'm doing here? So I'm saying, I know the concentration of chains I threw, the surfactant molecules in solution. I know it forms monomers, dimers, trimers, so on and so forth. The fraction of surfactant, all those different entities is given by that equation in the box. And by solving for that mass balance constraint, I can get x1. Once I know x1, I know all the other mole fractions. Okay? Satisfied up to now? Is the concentration of stuff I threw in. And that's a known, the x's are unknown. That's why I use x. I'm not doing anything yet. I mean, I'm just saying that Srikanth, look, I'm starting with entities that want to form rods. Okay? The concentration of those guys is C. Okay? Why are you bringing chains up here? N is the number of objects in my assembly. It's the cluster size, right? And it's the number of these little beasts that form together, that rod, the length of the rod is N. So what does that have to do with surfactant? I'm missing something. Yeah, explain. Yep. No, it depends. I'm only doing P equals 1. At the moment, this is only P equals 1. Thank you. Thank you. My mind is... I'm not... Thank you, guys. I mean, without friends like you, I don't know what I'd be doing. Can I move? Everybody understand the confusion here? So here's what I did. I said the generic form was this stupid thing, right? And I then went back to doing the rods, which is P equals 1, right? Because I think P equals 1 is easier. We'll come back and do the other P's later. I did that in my head. I didn't tell you I was doing it. I just assumed you guys followed along, and Srikanth said, no, I'm not following along. And I'm like, I don't know what you're not following along. Oh. That's it, yeah. That's right. We'll come back to that in a minute. You guys all okay if I move? So this thing is not hard to do, right? Let me just, for convenience, call that W. And so I'll write this in the following way. Don't want to do that. That's a well-known geometric series. From 1 to infinity. And say what? Yeah, so it's just saying that the concentration of monomers I throw in is going to be the monomers plus dimers plus trimers, whatever is left in solution. So I'm just summing that up all the way out to infinity. And then I'm just going through the mathematics of solving that infinite series. Any other things? I'm glad you guys are awake. You know, it's more than I can say for myself. I have an excuse. I'm still jet lagged. Or so I convince myself. As I get to what? As I get to... No, when you start with basically a 0 IQ, it's hard to go lower, right? It's sort of flat at that point. No, that hasn't happened yet. So this is the problem. When you stand up here and you wear the clown suit, people make fun of you and you have to take it, right? Everybody following along what I've done here, this is just a stupid geometric series, right? So let me plug back into this thing. W, this is, guys, wake up. So W is x e to the epsilon. I can plug that back in there. So it'll give me x1 divided by 1 minus x1 e to the epsilon squared. And this, finally, is a highly implicit solution for the fraction of free monomers or surfactants in solution when the overall solution concentration was C. Okay? So look at this. This is very nice. If x1 is small, x1 e to the epsilon, I say, is small. That means the denominator is basically 1. The concentration is all free surfactant. Tells you it doesn't want to aggregate when I have very low concentration of surfactant. Entropy wins. The chains are sitting by themselves. I start adding more and more surfactant. x1 starts to go up, but this denominator also starts to get smaller. There's going to be a singularity when x1 e to the epsilon goes to 1. Okay, and that's sort of the critical micelle concentration. Okay, yes? So look at the denominator, right? Because if it becomes larger than 1, the whole stupid thing blows up anyway. Because you know that if x1 e to the epsilon is greater than 1, then the mole fraction at some point is going to become larger than 1. That's not feasible. Yeah? It's a good question, thank you. But yeah, the radius of convergence for that is W less than 1, but that's also the only physically meaningful situation because I'm dealing with mole fraction. Never assume I've told you what you need to know, because I probably haven't. The question is, how do I solve this equation, right? So I'm going to go near the CMC or beyond the CMC. And at that point, you know that x1 e to the epsilon is almost exactly equals to 1. Because you know e to the minus epsilon is the critical Micel concentration. Okay? So what that basically tells you is this quantity is going to be small. So as a convenient way of solving this, I will call that quantity delta squared. And x1 is going to be e to the minus epsilon, close to the critical Micel concentration. Yeah? You're following along, you look puzzled. Struggling or are you keeping up? Okay. Anybody having trouble with what I did? Yeah? You're smiling in a way that makes me worry. Say it. No? You sure? All right. So that tells me that delta is 1 over square root C e to the epsilon. What it tells you, the concentration x1 is going to be, I said 1 minus this guy is delta. So let's just stop and think about this for a moment. E to the minus epsilon is the critical Micel concentration. Okay? So it tells you this is the concentration over the critical Micel concentration. That's a number larger than 1. So this whole quantity is going to be smaller than 1. And this is the critical Micel concentration. So it tells you the mole fraction is always going to be smaller than the critical Micel concentration, and it's going to asymptotically approach this concentration. Right? Pretty satisfied. So it tells you it's really bounded from above by e to the minus epsilon, which is sort of what I'd intuited before, but this mathematics proves that. So what am I trying to do here? I'm trying to prove that I'm going to get, I've said this to you before, that the concentration comes up and flattens out to the critical Micel concentration. What I want to know is, can I get finite size objects like this picture claims you should be doing? So if you think about the physical situation, the aggregation number should be something nice and positive. So what I need to do is calculate xn and see if it has a maximum. That's the strategy next. Can you guys still see here, or am I too far? All the way at the back. Can you guys see? Yeah? Okay. So this is just a matter of plugging in, right? So xn is n x1 e to the epsilon all to the power of n. You plug that in there. You get this. And that, for a good approximation for large n, yeah? You have a question? Oh. Which one now? That cancels out, right? The e to the minus epsilon, e to the plus epsilon cancels out. I'm left only with that term in the bracket, and I raise that to the power of n. If this quantity is very close to 1, then it's just the definition of the exponential of e. Which one? Yes, 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 yes. Everybody satisfied? Mm-hmm. So here, x1 e to the epsilon is correct. I plug in for x1, which has got that e to the minus epsilon. That cancels with the plus e to the epsilon. I'm left with only this guy in the bracket. Oh, sorry, you can keep that. Sorry, you're right. But see, it has no n dependence. That's why I don't care about it. But you're right, I should keep that. All right, so that's the number fraction of n-mers. And if you want to see if there's a typical one, you look for a maximum. And when you do that, you come up with this very nice, simple result. Well, e to the alpha is e to the minus alpha is the critical mass concentration. So it's the concentration over the critical mass concentration. So it tells you if I'm at a concentration which is 100 times the critical mass concentration, I can get clusters of size 10. This 10 to the 4, you get clusters of size 100. It tells you as I increase the overall concentration of surfactant, the cluster size increases. Which is sort of okay, because there's a finite size. But it's not in line with this intuition, right? Because this intuition says I form a micelle that is only determined by the head-to-tail ratio. That's the critical packing fraction idea that we came up with, that tells you the tail was a certain size, the head was a certain size. And that sort of defined the geometry of the object. This is telling you that the geometry of the object depends on the concentration. The higher the concentration, the bigger the clusters that you form. So it's got some parts right, but not all parts. Everybody understanding what I said? Srikanth, you look surprised and happy. And why is that? I did ask before I started writing. Which can you not see? So it says it's root of C over C subscript CMC, critical micelle concentration. Yes? N subscript max equals square root C e to the alpha, which is approximately square root C over C subscript CMC. Yeah? What's the matter, guys? Should be what? It doesn't matter. It doesn't have an independence, right? So who cares? Just stick it in there. That's just going to be another critical micelle concentration. Fine. It's some number. We don't care that much about that. Yeah? Again, remember, I'm ignoring all sorts of prefactors, right? I mean, this is just a scaling argument. So you just want to see physically if it tells you there's a cluster that forms and how does it change with concentration. It tells you it gets bigger the higher the concentration, right? But it does form finite size clusters.
What you're saying is that the geometrical cluster size.
Correct.
This is just
right. That's right. But the good side is that it does give you a finite cluster size, right? So it turns out if I use these other forms, right, P not equals 1, I'm not going to go through the mathematics. I can do this whole machinery over and make 100 more mistakes, right? But you will end up with an answer that says the critical cluster size will go like 1 over epsilon squared, or epsilon to the 1 over P, something like that. The problem with this is because epsilon is a number greater than 1, for any P that corresponds to spheres or cylinders, you will form clusters which are smaller than a monomer, which is complete garbage. You guys following what I'm saying? Yes. I will repeat it as many times. Give me a second. Anybody else have any other questions? Except for please repeat. Yes. Okay. Which contradiction? The first one or the contradiction? Okay. So remember yesterday I was talking about this packing parameter that said that the surface area of the head, the tail determined if it was 1/3, it forms spheres. If it was a half, it forms cylinders, right? So if it's forming spheres, it basically tells you the heads are too big relative to the tails. And so that sort of defines for you what the aggregation number should be. Because if the head is mongo big and the tail is small, you can't put so many molecules together. So in some sense, the aggregation number is defined once I tell you what the surfactant molecule is, right? This is telling you, no, 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 no. If I put more of it, the aggregate actually gets bigger. Right? So, in one hand, you're saying the geometry of the surfactant decides the aggregation number, and the molecular thermodynamic tells you, yes, you form clusters, but their size is not defined by the geometry of the molecule, but rather by the overall concentration. So those two things don't make sense. That tells you the geometry of the molecule got lost in this argument. Yeah? Happy with the contradiction? Okay. Going back to your question, what I said was the following. I defined this for P equals 1. Right? All that derivation I did was P equals 1. Okay? I can go back and put P equals a half, which is for a disk. Okay? If I redo that whole calculation and do the optimization, I will get an answer for N max that looks like that. Okay? If P is a half, that means it goes as 1 over epsilon squared. Epsilon is greater than 1. That means N max is going to be less than 1, which is stupid. So it tells you, for anything but rods, this model will predict the monomers is the most stable state. So this thing is wrong at many, many levels. It sort of gets the aggregation number, right? But that's about it. Tells you that you have a maximum aggregate number, but that's all. So what's missing? You following along, right? You're just smiling like I'm making mistakes, or are you laughing about it? It's missing because it turns out this is more dominant than that one, yeah. So what's going on, guys? How do I fix this problem? Surfactants you throw in form micelles. We know that. It's known. That's how you guys take a shower. We've gone over this last time, right? Yes, Srikanth. Everybody understand what he just said? Okay. What he said was that the important thing here is that you used a model for mu and zero, which was a purely energetic argument, right? And it told you that as the clusters grew bigger, your mu and zero only accounts for the missing neighbor. That is accounting for the head group's interaction with the water. It is completely missing the tail. Right? There's a part that loves the surfactant, the water. There's a part that hates the water, right? So it cannot just be one piece that defines mu and zero. It must have a head contribution and a tail contribution, okay? So it doesn't distinguish between head and tail, and that's clearly one problem with the whole issue here, right? What is the tail doing? How is the tail coming into all this? How do you think the tail is going to add to the chemical potential? Everybody, all of you following what I've said up to now? You following my argument? Sort of? Where do you get lost? So what Srikanth basically said is that you're only accounting for the heads, right? So the tails have to be accounted for, right? We've not done that. We've not distinguished between head and tail, and that's what we got to do. So if you understand that, then I'm going to ask you, how do the tails contribute? How do I think about this tail? So the head group has attractions to water, so you talk about missing neighbors and all this stuff when you pack, right? Which is what that argument is for forming rods. The surfactants are on the tails are inside the micelle, right? So how do I think about this problem? Is it an energetic problem? Is it something else? Yes. Excluded volume. That's a very good thing to always remember. Yes, you're right, but it's more than that. He says entropy. Does that mean anything to you guys? Why should I think about entropy in this context? So remember the problem. I have a surfactant, head group, it's exposed to water, tails on the inside. Why are you guys laughing at me? It could also be obviously wrong, right? But gee, I'm the sort of guy, if you say entropy, I will say entropy Y, right? And then these guys are going to look at me and say, what's the next information? Or what's the other one? Organization? So why isn't... Exactly. So eventually, otherwise, I'm not done with my lecture, and that's when, you have to go to sleep, right? So why is entropy playing a role here? Why not? Any other thoughts except that intelligent one, or why not? So let's draw this guy out, okay? Let's just think about those surfactant tails, right? Think about this. The surfactants are doing this. Okay, that's one possibility for the surfactant. The other thing it could do is it could do this. I know I'm sort of overdoing it, but which is better for the change? Can you tell the difference between my two drawings? It may be hard to tell, right? Okay. So both of them, the head groups are completely sitting on the surface, right? They more or less have the same aggregation number. But in which ones are the tails happier and why? In both cases, the tails are only seeing tails, right? So energetically, they're athermal. Yeah? The head groups are seeing water in the same way. So it's athermal from that point of view. So the only difference in one case, the chains are all stretched. In the other case, they're all like a bowl of cooked spaghetti. Which one's better? Say what? I think you're feeling hungry. That's why you like that better, right? He says the dangly one because why? Conformational entropy. What does that mean? Okay. So think about it this way. You're exactly correct, right? So think about the molecules when they come out straight like that, right? So that means they have exactly one way of being put in. It's like a stick. Okay? On the other hand, on the right-hand side picture, the chains are able to go in many different ways. So there is many more different ways in which you can realize that state on the right. The chains could go one way at one time to the left, the other time to the right, and you can have the same state energetically, but the conformations are going to be different on the right than the left. So which is preferred, the right or the left? And why? See, she got the lesson. The entropy is going to favor the right side. You guys following this logic? So what I'm going to argue is that the Israelashvili book from 1976 completely misses the entropy of the tails, which is what drives the structure on the right. Now what that means is I have to figure out how to calculate the entropy of that chain on the right. And that's going to be what we do for the next hour and a half, that you guys are going to be here. No one going to say something? I said an hour and a half, and everybody said, yeah, sure. I mean, I'm saying what? No, you're not. Yeah. So you're asking an excellent question, right? So here the things are sort of vibrating locally, right? Here it's sort of conformationally going all over the place. So if the density gets too high here, then you're absolutely correct. But it turns out that between here and here, there's enough play in density that I can increase the density a little bit, and the conformation entropy gain is enough that I can tolerate a little bit density gain. If you push this argument out to the extreme, eventually it's going to vitrify, and then the whole advantage goes away, right? And that's one of the reasons why polymers will eventually crystallize. If you drive them hard enough, right, that entropic gain is not enough to overcome the energetic advantage you get by lining things together. So at low enough temperature, entropy doesn't win. Energy wins, you crystallize. That's why paraffin wax at very low temperature crystallizes. When you heat it up, that thing wins and it melts. It's always a balance, right? So it can crystallize, it can vitrify, but it can also give you that structure. And for a surfactant micelle, it turns out at room temperature, you're close to melting, right? Because the chains are C16. If you had a C100 surfactant at room temperature, you couldn't take a shower. So that's why they use C8, C10, C12, because that'll melt, okay? So one, I'm sort of making it appear that the geometry is set. It's not, number one, because that's a balance of energy and entropy, number one. But number two, it's telling you that these two states, okay, energetically, the number of head groups on the surface is exactly the same. So head group water interaction is unaffected. In terms of tail-tail interaction, it's exactly the same here too, because it's the same number of tails and the same distance. So energetically, they are isomorphic. So then you ask what else could be favoring this state, and the argument is it's the conformational entropy of the chains is larger here than there. So given a choice, free energetically, that's a lower state, it will go there. Yes? You sure? Yeah. I mean, the glib answer is you put everything in and let it come out the way it does, right? But clearly you ask. So what we guys do is we're always inspired by physical reality. In physical reality, with a soap molecule, you know the maximum tail length is C16. The C16 melting point's around 20 degrees. You're going to be showering around 30 odd degrees centigrade. So you know the tails are going to be molten. So the physical situation those guys have found in the lab is that that kind of length works. They don't make it with longer. That means they must know something. So that tells you that the conformational entropy of the chains really matter in their formulation. So we are inspired by physical reality to sort of tune the appropriate parameters. Is that a bad answer? Right. No, so we started out, and the theory of Israelashvili only gives you finite size clusters for linear aggregates. Okay? So we already know that for spheres and lamellae, the Israelashvili formalism does not give you a stable aggregate. Okay? So you know something else has to be inspiring you. So that must be a factor that's been ignored. And so that must be the entropy of the tails. So there's many reasons why you come to the same point, but they're all driven by experience that the experiments are telling. In what case? In which case are you talking about? Oh, the rod case. But see, he set up a problem where he did only energetics. Well, he would have had to do a lot of work by saying I have a surfactant tail and it's doing something, and then I have to find the other surfactant tails and do all this kind of stuff. He didn't bother. So he wrote a model that he could solve. Okay? And right. So no, he didn't do that. I mean, this is what many scientists will do. They will write a problem they can solve. So you take the problem, you solve it out honestly, and you say, this doesn't match experiment. So then you say, what is missing, and you go back and put that piece in. And that's what I'm trying to do. Yes, everybody happy with this? So how do I put in the entropy of a chain? This is sort of a very important canonical problem. Yes? No, but see, he's picking a molecule, he's picking a case where he has these objects that come together to form rods, and the only energy you gain is through rod-rod interactions. So there's no surfactant tail, there's no molecular detail, right? So this is some cartoon model that he says he put in that he can solve. Right? So what I'm going to do now is solve the problem of the conformational entropy of a polymeric coil. And this turns out to be a problem that won Paul Flory a Nobel Prize. And it's so elegant, it's so beautiful. I'm going to do this. And there are lots of terms people use that I want you to take away. I'll sort of give you where these terms come from. I will still not solve the surfactant problem today because I think I don't have enough time. The goal today is to try and tell you how to calculate the entropy of a polymer chain. And from there, start to calculate free energies and stuff like that. So a polymer chain is going to do that. Okay? Now remember, it's made up of carbons and hydrogens and all that kind of stuff. So really, if I was to draw it, it was going to look like this. I will still have to maintain that carbon-carbon-carbon bond angle. But then it can do stuff like this. You guys satisfied? Yeah? What's wrong with that picture? What? Bond angles are fine. I drew it badly, but you can draw it better. I mean, don't criticize. Don't learn from him. He's a bad example. Don't look at him. Imagine I could draw the bond angles just right? But it can still kind of come around and do all this crazy stuff, right? What's wrong with that picture? Say what? They are ghost chains. What does she mean by that? That's right. So the chain is intersecting itself. Is that allowed? Can a chain ever cross itself? Why is that not possible? Say what? No, in 3D. It doesn't matter what D you're in. If I can cross myself, can I have two monomers at the same place at the same time? Yes or no? So I cannot really represent a chain as a ghost. Can I just have a random walk represent a chain? Yes, no, maybe. Everybody understanding the question? I have a polymer chain. It's just carbons and hydrogens. I'm drawing it in its state where it's random, right? And I'm drawing a cartoon where it sort of comes and folds back on itself and crosses. That's my depiction of what a random walk polymer chain should look like. And immediately several people pointed out that means two monomers or more may be at the same place at the same time. And what do you say to that? Everybody says, nope, not right. So what do I do? I mean, this is the problem I want to solve because that's the problem that's easy. If I start doing a self-avoiding walk, it's hard. Yes. Mine comes from ignorance too, but that's okay. Go ahead. Yeah. Because you're doing in 3 dimensions, right? So you start, the first 3 bonds are in this plane, the 4th one will twist out, and then by twisting you can come back. Yeah? By torsion you can come around, no problem. Yeah, in 2D it's hard to do, but in 3D you can, very easily. It's coming out of the plane and then going back. Yes? Over a long enough, so it's called a persistence length, even DNA, double-stranded DNA, over a long enough length will bend. We know that. Yeah, imagine you're far enough along that the chain sort of is forgotten its chemical detail, it comes back and folds happily on itself. Don't get technical. I'm now forgetting about that problem. We'll come back to reality later, right? We've got to do the abstracting for a bit. Any other criticisms? Any other things that I'm doing wrong that you want to point out? Everybody happy? Some people are going to sleep. You're the first guy who dropped to sleep. You know that? So how do I solve this problem? I mean, I want to do a random walk, right? Say what? Yeah, that's what a self-avoiding walk is. But then the chain, I want to do it as a random walk because I know how to do random walks, right? If I want to do a saw, I have to, in very detail, remember where the conformation was. It can never come back and fold on itself. I can do that, but it's a freaking pain in the neck. I would rather just deal with a random walk because I'm lazy, okay? It's also like a spherical curve approximation. You know how much we love that, right? So this is what Flory realized, and this is a very important thing. I think Chandan sort of pointed it out. What is this guy called? U is the potential energy between 2 monomers, right? So that is a pairwise interaction. E to the minus U over KT minus 1 integrated over volume is the second virial coefficient. Okay? So it turns out, this is sometimes called beta, it's called V excluded, whatever you want, right? This is called the excluded volume integral as well. So if you imagine you have a hard sphere, right? Or actually it's done the other way around. I would prefer to do this because it'll come out nice and positive. So let's look at this potential. All right? So let's do 2 monomers, which are hard spheres. The diameters are sigma. Okay? So if you go below the hard sphere diameter, U is infinity. Above that, it's 0. So I can break this into 2 pieces, 0 to sigma, sigma to infinity. I have a 4 pi here. I have an R squared. When U is infinity, that thing goes away, and I get this quantity. Beyond the hard sphere diameters, U is 0. This exponent gives me 1, and this integrand gives me 0. So if you do this integral, you will get 4/3 pi sigma cubed. So this quantity here, that integral of 1 minus e to the minus u over RT, tells me if I take a sphere of diameter sigma, the center of a second sphere is excluded from a volume which is 4/3 pi sigma cubed, which is basically a sphere that is defined this way. This radius now is sigma, And that makes sense because the center of the second sphere cannot come closer than that point, and that's the excluded volume. Everybody satisfied with this? Okay, so if I take two hard spheres, they can never be at the same place at the same time. We know that, we love it, everybody appreciates that. Now, real monomers also have attraction. So I'm going to make that complication a little bit more, and let me redo this excluded volume. This is now going to be my new potential. This is sort of extending what Chandan was talking about yesterday. This is sigma. Let me call this lambda sigma, and this well depth epsilon. So this excluded volume parameter now has three contributions, 0 to sigma, okay, and there's going to be an R squared out front for each one of these. Here it's still the excluded volume. I get the same quantity. And here I get the same thing as before. Nothing has changed. But in this middle piece here, I get 1 minus e to the epsilon over kt. And if epsilon over kt is greater than 1, this quantity is now negative. So I have an excluded volume, I have an included volume, and if you pick just the right temperature, those two guys cancel. That state is called the theta state. It's also called the state at which polymers are in what's called a marginal solvent. And in that condition, the excluded volume exactly goes to 0 in an average way. Everybody following what I just said? Anybody didn't follow the argument? Yes. What didn't you follow? I can repeat myself, but the question is, what did you not follow? Okay. So I'm defining this random quantity, right? 1 minus e to the minus u over RT. So it tells you, let me think about this quantity. And it turns out if I take two hard spheres, it tells you how much volume is excluded per center of a second sphere by the presence of a first hard sphere. That's what the calculation gives me for two hard spheres. Okay? You happy with that? That was the first thing I calculated. Then I said, let me think about two spheres that are hard spheres, but now have attraction at intermediate distance. Okay, and now what happens? Oops. Is that mine or yours? Okay, I'm getting excited. Right. So when you do that same calculation over, I still have the excluded volume because of the hard spheres, but the attractive part now contributes a negative term. What that means is that because of attractions, two monomers want to be there. Even though they're excluded from overlapping with each other, they would prefer to be a certain distance away. And if you pick the temperature just right, those two effects exactly cancel. So if you look from far away, it looks like the chain could cross, effectively. Following? That point is called the theta point. It's a very precise definition for a theta point. It turns out if you take a polymer solvent system, at the theta point is where chains are ideal. Above that, they're happily soluble. Below that, they phase separate. Okay, but that's another detail that you guys don't care about. Yes? Please ask, please ask. Say more. Say that again. I want to get to that point, right? But I want to start by canonically solving the problem where the chains can overlap each other perfectly. So even though in a very detailed way they cannot cross, they can look effectively like they can cross. And that's the model. Yeah. Yes. It'll be finite, exactly. But it's telling you that rather than being all over the place, which is what a random chain would do, so a hard sphere, only thing it says is, I can't overlap you, but I can be anywhere else equally. In this case, because of attractions, I can't be anywhere randomly. I would prefer to be close by. And if I pick it just right, the prefer to be close by exactly cancels the fact that I cannot overlap. So on average, it looks like you can overlap. I understand the problem. I understand the problem. So this is looking from far away. So I don't know any chemical detail. So a random chain would be like happily going around, except this region that's excluded. Because of attraction, it cannot be random. It prefers to be close by. And if you pick it too strong, right, the chain wants to always be here, it'll crash out a solution, right? But if I'm just at the right point, this exclusion and this inclusion appear from far away to cancel. So the chain almost looks like it crosses itself. I know you are confused, but go ahead and ask. I'm going to sit down because, yes. Correct. Yes. Basically, at the point where you're going through phase separation, at the critical point, right? It turns out it's at the critical point, you still have entropy, right? But at some higher temperature called the Boyle temperature, it appears as though molecules effectively have no excluded volume for each other. You feeling better, or should I continue to sit? Yes. No, but you're correct in terms of separation. Just two monomers, right? So, in a given, if it's a 2 hard sphere thing, right? It just cannot be excluded. Okay, but apart from that, it can go anywhere happen. That's a consequence. This is a very detailed molecular level thing that I'm trying to convince you of. That it sounds idiotic, but there is a particular temperature at which, on average, it looks like excluded volume is zero. And then I can treat it as a random walk. It's like religion. He doesn't like it. But so I'm going to assume you guys followed this concept. If you don't, you'll jump up and down. It's 12. What time do I have to end? 1 o'clock. Okay. This is going rather slowly, but that's all right. So this condition where the excluded volume cancels out, I'm going to say the chain behaves as though it's a random walk. And this is a very important answer. Okay? Yes, Srikanth. Correct. Absolutely. That's the supposition, right? I mean, so it turns out that even if you go to the theta point, and a lot of people like Duplantier think about this, that the third virial coefficient now comes in and expands the chain a little bit. So even though the second virial coefficient goes to 0, the chain is still not ideal. You have to go to a slightly lower temperature, so the second virial coefficient becomes negative enough to overcome the third virial. And I mean, this is going to go on ad infinitum, right? Because as I add higher and higher orders to the virial expansion, I'm going to have to progressively go lower and lower for my chain to appear ideal. And everything, absolutely. This is a two-body level of an approximation. You're exactly correct. But that's the Flory approximation. Okay? And that's why I wrote this two-body term. The second virial level is where this is valid. It's random walk at that level. Everybody happy with the technical detail I've gotten into? Who is like totally lost it here? So remember what we're trying to do. We're trying to calculate the conformation entropy of a chain, right? That's sort of the idea. And I said the only model I think I can work with is a random walk. And now I'm finding a condition at which this random walk is more or less satisfied by a chain, and I'm going to work under that condition. So these ideas are going to work only under that one condition. Yeah? So what we're trying to do now is try and figure out what the conformation of this chain is going to look like. Are you asking a question, or are you just scratching your head? Just scratching your head? You're following, right? So this is a 3D random walk that I want to think about, right? But I'm going to start by saying if it's 3D and it's a random walk, it's random in all three directions. I'm going to deal with a 1D random walk first, and then go from there. Can I clarify? You guys good? You sure? So let's do this problem, guys, and this is very quickly going to tell you where I'm going with this whole thing. So let's start. I have a 1D problem. I start at the origin, and I take n steps. And the only thing I'm going to do is I can go backward and forward with equal probability. Okay? So I take n steps. All right? And they talk about a drunken man or whatever doing this thing, walking one step and then going either forward or backward with equal probability. That's a random walk in one dimension. And for a drunken guy or gal, excluded volume is not an issue, right? Because they are only in one place at a time. So it's still fine. So n plus minus n minus, what is that going to be? You say something? Huh? It's a drunken man, right? Take a large number of steps. What's n plus minus n minus going to be? Distance. But what is the expectation? How many of you have gone to a bar after drinking one too many and tried to get home? Did you actually make it home? Think about it. If it's a completely random walk, n plus and n minus are going to be equal, right? Because you make forward and backward steps with equal probability. So the first thing you realize is this guy ideally should be 0. That's the ensemble average value. But the fluctuation is going to be a small number. We call that x. And so this is a very important thing because for a polymer chain, this tells you the end-to-end distance in one dimension. And the very first realization you make for a random walk is that it's going to be much smaller than the number of steps. It's going to be close to 0 is the expectation. Why should I bias myself? I'm a totally fair person. Why do you ask the question? No. N plus minus n minus equals x. The expectation value for x is 0. The mean value is 0, right? But I'm saying what is the probability that I can find x not equal 0 is what I'm going to be going for. Because it tells you the most probable value for the chain ends is going to be this. But if you think about the problem we're going towards, the chain is being stretched, so the ends are not at the same place. So I want to understand what the probability is of separating those chain ends away from that most probable value. That's what I'm trying to calculate. Yeah? Everybody satisfied? So if I'm going to make n plus steps and n minus steps, how many different ways can I do that? That's this guy. You might think this is the only thing I know how to do, and that's pretty close to the truth. So you write this out. This is the number of different ways you can make a random walk so that you end up with an end-to-end distance of x. And x can be positive or negative. So this guy is the number of different ways by which I can end up with an end-to-end distance of x. So this should be proportional to the probability of finding a separation of x for the units. The most probable one is going to be x equals 0, but I want to understand how to stretch it. And that's what I'm going to try and calculate. Everybody following the strategy of what I'm doing? Yes, no, maybe? What do I do now? Several things become obvious, right? So the entropy of this particular state is going to be, so S of x, which is the entropy of a state where the chain ends are separated by x, will be the Boltzmann's constant times log of omega, plus some constants to make sure the probability goes to 1 as well. This is not going to help, right? Because I can do that, I can do Stirling's, and I'm going to end up with this mess. So as I'm writing this thing out, I want you to think about what do I do next to make my life easier? That's the entropy associated with taking chain ends and separating them by x. And so remember, I'm trying to figure out the entropic cost of stretching chains. So all the physics is there. But I want to make this thing tractable. And the question is, how do I make it tractable? Any thoughts? Why is what? Why is what? Look, if I go and give this to a second-year undergraduate and ask them to do this logs and stuff, it's kind of stupid, right? I'm wondering if there's a smarter way of doing that. Is there anything intelligent I can do with this thing? So first, you guys know this in math. First thing is you do Stirling's. What's the next thing you do after that? What's the mean value of x you expect? What are you telling him? You're not allowed to help him. What did you say? Yeah, how do you get Gaussians? There's another way of thinking about it. Oh, think about it. Is x a small parameter here? Relative to n? So when you have small parameters, what do? Taylor expand. Good. Do the Taylor expansion. And I'm not going to do it. I'm lazy as all hell. But if you do the Taylor expansion, this will give you this quantity. Plus some constant. So this tells you that the probability of finding a random walk where the end-to-end distance is x is going to be some constant, which I'm going to call, I don't know, k, e to the minus x squared over 2n in 1D. All right? This is, as Bulbul said, a Gaussian. Now, this doesn't, imagine now, I'm assuming that the step length is 1, right? Inherently, I'm saying a random walk, you're making steps of length one way, one on either side. A real polymer may have a step length that you write that. B is the step length of a real polymer chain. X now has units of length. This is just a thing we do to start making things happier. So for a Gaussian, this is now the variance, right? I mean, this is the standard deviation squared. We know that to be true, right? Say what? B is just instead of saying unit length is 1, I want to put 1.54 angstroms or something, right? To convert it to real length, which is what I'm going to need to go to my surfactant problem. So to start making contact with reality, I have to put real units. So that's all I'm. No, he's perfectly awake. This is the stuff, if you haven't seen this before, you're wondering what kind of tricks he's pulling, right? So let's ask the following thing. I want you to calculate the mean value of x from here. What do you think that's going to be? Say what? I can't hear. Right, what do you think that number is going to be? Come on, guys. Length of the polymer, that's what you think. Go back to the drunken man's walk. You went forward and backward with equal probability. What is x bar going to be? 0. So put that in. Go from minus infinity to infinity. It's x e to the minus x squared from minus infinity to infinity. That will give you 0. Because that's just e to the minus u squared. Do the calculation, make sure you agree with that. First thing. So it has to give you the right answer that the mean end-to-end distance is going to be 0. So if you ever go to a polymer conference and somebody talks about the mean end-to-end distance and has a number that is not 0, you can stand up and say, sir, you're full of shit. You're wrong. And this is not an abnormal mistake. People do it all the time. All the time. Because what they'll do is they'll take the absolute value of x and take an average of that. That's not the same as the mean value of x. Because it's a random walk, this has to be 0. What do you think this is going to be? Thank you. And this is a central result in polymer physics. The mean squared end-to-end distance of a random walk polymer chain scales as n, or the root mean squared end-to-end distance goes as square root of n. So if a polymer chain is of length 10,000, its fully stretched length is 10,000. Its random walk, most probable distance for the end-to-end distance, is going to be 100. So a chain is awfully small relative to a fully stretched chain. Okay? And this, therefore, when you go from the completely random walk to a fully stretched chain, that's where you're losing the entropy. You guys following all this? Yeah? So if you like here, at the end of the day, the effective result that I've derived for you, if I take log of p, which is here, there's a bunch of constants that I'm not following. It's going to be x squared over 2 times that guy. And there's a minus sign. This is in 1D. Why do you look puzzled? Yes. What log term? I just did it. You see the probability? Log of the probability is the entropy. So it gives me minus kx squared over 2 times the expected value of x squared. What's the matter? I know what they're thinking about, but I want them to articulate that. Why is there no p log p? So that's an assignment problem for today afternoon, right? So let's leave that. I just went through this analysis and I showed you that for a Gaussian chain, the entropy is basically the log of p. Okay? And it's not p log p. Why did I do that? Think about that. Remember also, when you do, if I say it, I'm going to give away the answer. This is the entropy of a particular state. So if I take a chain and I make the end-to-end distance bigger, its entropy goes down by that quantity. That's what this is telling you. So the further I stretch the chain, the more the negative the entropy gets, the smaller the entropy, the more unfavorable it's getting. You guys following this? So this is in 1D, and it turns out if you go to 3D, okay, if I take a chain, if you're completely random, the ends are at the same place. The most probable value, which is the mean squared distance, will be x squared equals nb squared. If I start stretching it out from there, the entropy goes down with the square of the separation. So the further apart I take it, the entropy goes down quadratically. So it's very unfavorable to stretch this stupid chain in an entropic sense, just because the number of conformations go down. You guys see what I'm doing here. As you stretch the chain, number of conformations drop, therefore the entropy goes down. It's very, very, very unfavorable. This is in 1D. You can do the 3D calculation, which I will not assign to you. It turns out the mathematics is more hairy, but you can actually do it. And it's almost irrelevant, but in 3D, it looks like this. Minus 3 over 2 nb squared r squared, where r is now the three-dimensional distance. Vectorial distance r squared is a scalar. Same result. Many, many caveats here. First thing, realize this is a perturbation about x equals 0. So this is only valid for near Gaussian states. I'm going to go to the fully stretched limit. I can no longer use this approximation because it's a Taylor expansion that I'm taking out to quadratic order. And it turns out if you actually do the fully stretched length, which is relevant for things like DNA and stuff like that, a different kind of formulation has to be thought of. You start with the same omega function, but you do the expansion differently. It gives you Langevin functions, hyperbolic tangent functions. It's just a nuisance, but there's nothing new there physically. So this is the entropy. The free energy of the chain as a function of R. It's an athermal chain. Excluded volume is 0. The energetics are exactly 0. So the free energy, there is a K here, of course, I forgot, will be plus 3 kBt over 2 nb squared R squared. Please look at that formulation. What does that remind you of? It's an energy that scales as R squared. Harmonic what? harmonic oscillator, right? So this polymer chain looks as though it's a harmonic spring. Remember that. That's something that people use all the time. You can also calculate the restoring force. If I stretch it, that's nothing but the free energy derivative with respect to R, and that will give you this thing, 3 kBt over 2 nb squared. Or this again shows you it's a Hookean spring. So a polymeric chain, sorry? It's going to act like a Hookean spring. So a few things I want you to remember here. I make the chain longer. What happens to a spring constant? Yeah, as n becomes larger, what happens to a spring constant? Goes down. So is the chain becoming softer or harder? Softer. So going back to your C18 example, how big a deal is this going to be? It's going to be a very big deal because the chain is awfully, awfully short. So these entropic forces in surfactant assembly are going to be hugely important. Okay, that's point number one. Point number two, I raise the temperature. What happens to the spring constant? Goes up. So I'm going to do an experiment. I'm going to take a rubber band. I'm going to pull it with constant force, hold it. I raise the temperature. What's going to happen? Shrink. Do that experiment. That's actually what happens. So in contradiction to almost all materials, polymeric systems, when you heat them under constant force, will shrink. And that's a consequence of what is called entropic elasticity. So some very funky things. So your rubber tire works off that principle. The reason it's able to bounce and come back is because the chains in there are able to be distorted very easily. When you let go of the force, they come back. They act as though they are soft springs, which is why you can ride on those tires and be perfectly happy, because they're soft. You make the chains longer, they get softer. So you can control how soft your tires are just by controlling the molecular weight. These are very important physics things that affect your everyday life. Think about it the next time you drive your car. When you go over a horrible bump and your butt hurts, that's because the chains were just too short. The whole thing was too stiff. Okay? How am I doing for time? So this is all going to have to be brought back at the end, right? But I want to just sort of give you how we're going to think about this. You guys good? Yeah, I'm going to do that right now. We'll get to that. We'll get to that one by one. This is all single chain, right? Then you go to many chain. It's like when you get to many chain, you just sort of hand wave it away, right? You just say, it's, you know. You guys following what just happened here? So the free energy here of a chain looks like this. And that's the scaling formulation. That means I've now lost all my prefactors. I don't care about prefactors. I've lost my KT. I've lost everything here, right? So it tells you, it embodies the fact that as I try to pull the chain ends apart, it costs me free energy. And that's all I care about. The prefactors there, which we don't even care. So what I want to do now is start with this random walk and ask myself if I now remember the fact that the chains actually want to exclude each other. So let me go away from the theta point. I go into a condition where the chains repel each other. Okay? And let's say the excluded volume parameter now becomes a V, which is that integral of 1 minus e to the minus u over RT. I'm going to ask myself, what does the presence of excluded volume do to my chain? What do you expect is going to happen? So I started with a random walk, has no excluded volume. It comes out, it's a Gaussian chain. It's got entropic elasticity, all this stuff I just derived, right? Now I'm going to go back to the problem I really care about and say, let me put back this excluded volume, because this random walk chain only works under one temperature condition, the theta condition. Go to a higher temperature, the chain now feels excluded volume. And I do a simple fix and calculate what the end-to-end distance should look like. So remember, when I put excluded volume, the chains want to swell, right? Because they're avoiding each other. They say, I don't want to be this small. If I get a little bigger, I can reduce the number of overlaps. That entropically is unfavorable in that way. You agree? As the chain gets bigger, this is going to cost me free energy. On the other hand, if I make the chain smaller, this excluded volume parameter will become a larger contributor, right? So I need to figure out how to balance those two. I have n monomers per chain, okay? The only way I'm going to have contacts is if I find another monomer. So I have to ask myself what the probability is of finding another monomer, and that's going to be proportional to the concentration of monomers. So this is going to be the energetic term. You guys like that? You guys lost? You following along? How many of you are totally lost at this moment? Be honest, raise your hand, because otherwise I'm going to pick up. Yes. When did you get lost? Okay. That I can help. You're not lost like half an hour ago and just coming up to the surface and saying, oh, I'm totally lost. Well, that I can handle. Anybody lost beyond that, like 2 days ago? Seriously, this can happen. You follow along the first term, R squared over NB squared? Everybody happy with that, right? So now I'm saying I have excluded volume. Excluded volume only happens if two monomers come together at the same time. What is the probability of finding two monomers at the same time? I find a monomer, and then with probability proportional to the concentration, I can find another monomer next to me, right? So this guy here, if I pick a monomer, the fraction of contacts that it's going to give me overlap is going to be proportional to the concentration, which is n over r cubed. I have n monomers. So this is the probability of the total number of contacts, excluded volume contacts, that a chain has. So this tells me to reduce excluded volume, the chain wants to get bigger. Because as R gets bigger, this quantity becomes bigger, this whole quantity goes down. On the other hand, the entropy doesn't like that. So that's the balance. Yes, you have a question. Look, I find a monomer, I pick a monomer, I want to find another monomer, that's going to be proportional to the concentration. Right? Uncorrelated. I don't want to do that. I'm saying I'm sitting on a monomer. No, that cannot be, because you're saying I'm picking randomly points in space and asking what the probability is of having a pair. That's the concentration squared. I'm not doing that. I'm saying if I'm sitting on a monomer, what is the probability of finding another monomer? That's only proportional to the concentration. The general question saying, what's the probability of finding binary overlaps somewhere in space will be rho squared, right? But that's not the calculation I made. You happy? Everybody satisfied? So let's do this minimization. And notice, as usual, I maintain no prefactors. I solved this problem, and this is an extraordinarily important result. Okay? This tells you that the scaling of the chain end-to-end distance because of excluded volume went from n to the 1/2 to n to the 0.6. Now you're going to stand there and say, who cares? That's a 0.1 change in exponent. Your chain length is 10,000. That's going to make factors of 20, 30, something like that. So a chain can really swell relative to the Gaussian state, but it's still a perturbation about the Gaussian state. Now this scaling exponent of 0.6 was a Flory exponent that was derived in the 1940s. People have gone back with renormalization group, done the full calculation, the real exponent, Lejeune worked out is 0.588. That's why Flory won a Nobel Prize and I didn't. You guys following along? I think I'm done. We'll come back and now figure out next time how these kinds of scaling ideas, where you're balancing the Gaussian entropy with energetics, can be used to start dealing with things like micellar structures, Rocco-Polymer structures, and so on and so forth. Because in the end, that's what I care about for self-assembly. But this is a crash course in polymer physics I gave you in 30 minutes, more or less. Any complaints, Srikanth? No? Okay. Any questions? Yes. Say that again. Yeah, but see, very good point. But if the excluded volume is still 0, right? If it's still a random walk, that would change B, right? But it wouldn't change the scaling exponent. It would still be n to the 1/2. Okay? The idea here is by putting in excluded volume, the scaling exponent goes from 1/2 to 0.6. Of course, we're not even going to go. You following? So it's more than just mean separation. It tells you the consequence of chain length makes the chain swell more and more the longer it is relative to the Gaussian chain. And in an n-dependent way. Whereas what you're saying will be n-independent. What do you want to add? Correct. Where do you want to put it? Right. But that's what's accounted for here. So this quantity is telling you the mean separation of the monomers changes because of excluded volume effects. Okay? If you change temperature effects, in the apps, if it's still theta-like, then this term doesn't exist. The B will change with temperature. That's sort of trivial. The chain is still going to go R squared equals MB squared with a larger B. Okay? So that's really you're asking a very important question. So by changing temperature, two things happen. One, B increases or B changes. That will change the prefactor, but the presence or absence of excluded volume changes the n scaling. So they affect it in different ways. So it's really profoundly important, the difference. Yes? Right? Correct. Correct. So there's what you're asking is extraordinarily important. So if you think about it, there's a carbon-carbon-carbon bond angle. Okay, that's 109 degrees, 54 minutes, right? Then it turns out if you go to the fourth carbon, it turns out that that potential will allow you to have 3 states, one which is in plane, and 2 Gauss states which are out of plane. So the chain is actually highly correlated at that level. At the level of 3 monomers, it's totally correlated. At the level of 4 monomers, it's still correlated. And it turns out you have to go almost 7 monomers before it loses memory of the starting point. So that's called the persistence length of the chain. Or it's called the Kuhn segment length, after this guy Werner Kuhn, who thought of this idea. So these ideas of a random walk work for chains made up of Kuhn segments. So you make up segments, or think about them almost as sticks, inside which there's correlation, but these sticks are uncorrelated from each other. So that's how you map a real chain into an ideal random walk chain. Okay, and again, this only works when your chain length is 100 or larger. Because below that, you're very comparable to the Kuhn length. Right? So if you have 20 monomers, you're 3 Kuhn lengths. At 3 Kuhn lengths, you're not big enough to be random walk stuff. So these ideas really work in the asymptotic end limit. Okay, and so even DNA with a much larger persistence length can get mapped into a random walk. And that's what Steve Chu figured out and won a Nobel Prize for doing that. Okay? So all these things eventually will map into a random walk. You just have to know what the scale is. So within that scale, there'll be lots of persistence. And the stiffer the chain, the longer that length gets. So these are coarse-grained models, but it's a classical physical approach to doing it, right? So coarse-grained models work for scaling and stuff like that. But if you're going to actually make a salary, then you have to take care of all the details. Right? If V is negative, the thing is going to collapse. You'll go to a point, right? So if you do this calculation, it'll actually tell you R equals 0 is the result. Right. Then you fix that by adding a third virial coefficient. And when you do that, it'll still give you that the n to the 1/3 scaling, which corresponds to a complete collapse into a sphere with excluded volume, will be the right answer. So you have to know when you're using this, this is only valid in the excluded volume regime. If excluded volume goes negative, it doesn't work. Yes. Anything else, guys? We all effectively lost our way? You're still following along. Do you see the roadmap of where I'm going? I started with the problem of surfactancy, assembly, First did a Strelachvili calculation based on classical thermodynamics. It tells you can form structures, but the structures didn't make any sense. And we said that's because we lost memory of the fact that you have a tail and a head. I've now figured out that the tail has conformational entropy. It looks like a Hookean spring. The Hookean spring constant depends on chain length inversely. It depends on temperature linearly. So the higher the temperature, the stiffer it gets. The more stretched it is, it's less entropically favorable, right? So those are the things we just learned. And now what we have to do is assemble all these pieces to start figuring out what the structure of a micelle is, or what the structure of black copolymer forms. And that's going to be what I will do next time. And so bring this all to sort of fruition, so you can actually start to think about self-assembly in some meaningful way. That's the roadmap, right?